More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at Home, real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at Home is right for your child, visit mathnasium.com/at-home. Mathnasium at Home, changing lives through math.
Hi everyone and welcome to Mathnasium Schoolhouse. I'm just going to pull up your comments here. Feel free to, as always, let me know who we have here with us today. Your name and your grade, if you're a student, are greatly appreciated. There we go. Hello, hello. I see a few of you saying hello already. I sincerely appreciate it. Thank you. So we are going to be working on perfect squares and square roots today, and you'll see why I purposefully chose this topic for today on Monday, because of a lesson that I want to show you later on this week. So we'll see how that applies, and I hope that you learn something new today. That's always my intention, and if for some of you this is a review of what you've already seen in the classroom, wonderful. It's always great to practice in math, as we all know that. So we have a lot of us joining us today. Very nice. I see a 5th grader. I see someone that's 10 years old. Oh, in 4th grade. Very nice. Perfect. So this is a wonderful, wonderful topic for you to explore today. Let me know if you've even seen this topic before. Do you know what perfect squares are? Actually, that's something that you can maybe even tell me in the comments below. What are perfect squares and what are square roots? All right. Go ahead and share that with me. And we will get started by just looking at what those two terms mean. So let's see if anyone can help me out. Yeah, this is great for 4th graders. You can definitely explore this with me today, so not a problem. It's not outside of your capabilities. Don't worry about that. Let's see if someone can tell me, what do you think, what do you know about perfect squares and square roots? Okay. Or maybe, hi Albert, maybe you can tell me any numbers that fit into these two groups. What do we think? Okay, we're going to start to form a chart in just a second, or a table I should say, of the comparisons between the two. Hello, hello. So I'm going to tell you here, I'm going to switch to my whiteboard. I'm going to start to write it down, and maybe as I write down these definitions, you can share with me some examples that fit into these groups. So if I show you perfect squares, okay, we're talking about perfect squares and square roots today. So let me write those two down. 8th or 6th grade, absolutely applicable as well. Thank you for asking. Okay, so perfect squares, I might not write down the definition, but I'll say it out loud. Perfect squares, the first one here, are numbers that are a product of two numbers. Okay, hello, hello. All right. Whereas the square root is the number you get where if you multiply, oh, perfect. I'm seeing some examples. Thank you so much. Yeah, so we'll fit those in just a second. Square roots are those numbers you get where if you multiply by themselves, you get back to the perfect square. So we'll see that in just a second in a table. I'm going to fill it out with you here. We're going to fill out some of our basic ones. So let me maybe pull this up here, just over top. And I'm going to write up here, we're going to be looking at squares, right? And feel free to share with me some examples as you come up with them. So let me, just going to pull up here, the comments, perfect. So let's look at, the way that I'm going to write this is I want the perfect square here. I want you to see the relationship here. So perfect square, we're going to fit into this column here. And then we're going to look at that root number. So I saw an example already in the comments. I'll fill that in as they pop up. So let's look at a few here. Hopefully this shows up with my pen here. So let's say I want 0 times 0. I'm going to go 1 times 1. You guys can help me out here. 2 times 2, 3 times 3, 4 times 4. Now we got the 5s, the 6, 7, and I'm going to go all the way down to 9, just for now. Okay, we can extend it in just a second. So feel free to share with me what you know about these. So I see that the root of 9 is 3. Wonderful. Okay. Let's see what else. I'm seeing the square root of 36 is 6. Perfect. So I'm going to fill that in. So that means 6 times 6 is in fact 36. Beautiful. I'll fill in that 9 as well. What else can you help me fill in here? You guys shared with me. Oh, we got 4 times 4. What is 4 times 4? Fill that in once I see it. What do we have here? Starts with a 1. Okay, awesome. So how about you share with me what those perfect squares are? So we got 16 for 4 times 4. Let's go back here. 0 times 0 is 0. 1 times 1 is 1. There's our perfect square. 2 times 2 is 4. Perfect. Thank you for sharing. 16. 5 times 5. I'll fill that in for us. I haven't seen that just yet. That was a 25. 7 times 7. We have 49. 8 times 8. We have 64. And the biggest one on this page here is 9 times 9 is 81. We're going to keep this here. I want to reference this later on in the lesson. Beautiful. You guys are filling it in. Wonderful. Okay. And of course we can keep on going, right? I can find 10 times 10, 11 times 11, 12 times 12, and so on. And in fact, we'll reference some of those as well today. Okay. So here we can already start to see the perfect squares. And how did I obtain them? Well, I took the number and multiplied it by itself to get that perfect square. Right? Again, 0 multiplied by itself, 1 multiplied by itself, 2 multiplied by itself, and so on. Okay? So here we have examples of perfect squares, but we also can start to talk about the square roots of these perfect squares, right? And square roots, I'm going to show you here, we can show with this symbol. Let me make sure I'm seeing my screen here. So make sure that that's visible just in the corner here. And square roots, I'll use a different color for this, will be shown using this symbol here. Right? So let's see an example here. If you need me to slow down, what you can always do is rewatch these recordings later and pause them as needed, all right? Just have a few areas to cover today. So I'm just going to remove the term perfect square here and show you a few examples. So let's say I want to look at the square root of 36. Right? The way that I would show this is I would use the symbol over top the number 36, and I know that I obtain my 36 by multiplying the same number by itself, and that number is 6. So I have that the square root is a 6 here. Okay? And I can do that with any of these numbers that I have in this table here. If I take the largest one that I have just appearing here, I can say easily that I know that the square root of 81 is 9, and that is because I know that when I think, okay, some number multiplied by itself gives me 81, I know that that number has to be a 9. And so there is the square root of 81. Perfect. Okay, awesome. So some of you might already know this. It's a good review. The purpose of today is to really explore the relationship between these two, the perfect squares and their square roots, and to go above and beyond and to challenge ourselves to not resort to a calculator when we're trying to find the square roots of numbers, right? Because we know that there are some beautiful numbers out there that we can find the square root of very easily, right? Once we know our perfect squares and how to obtain them, then finding the square roots of these is fairly easy, right? We just did this in just a few minutes. So that's wonderful. But we, of course, know we're not always going to encounter these beautiful numbers, right? Sometimes we'll have to find the square root of 17, right? That's not necessarily the prettiest number to take the square root of, but there are techniques in place in which we can do that, okay? And I know that it's going to be definitely something that might be new to most of you, because I know that it was new to me when I first explored it. Because it's not necessarily something that we get to explore in the classroom because there's so many things to see. And of course, our calculators, right, our computers just can do this so much faster for us. Nonetheless, it's exciting to observe. So let me remove this. And we're going to remember this notation for the rest of today. And we're also going to remember the fact, if you just observe here, I kind of already mentioned it in a different way, but I'm just going to summarize it. Remember that if the number inside this square root sign, so we looked at 36 and 81, if it's not a perfect square, so it's none of these, for example, then its square root is not an exact whole number. because we've already looked at all the digits all the way from 0 through 9 and found their perfect squares. And so now we have to start to look at numbers in between these whole numbers, right? And then we'll be able to get their squares, but to find their square roots, it won't be so pretty. And that's what we want to work with today. Perfect. Glad you guys are having fun already. Let me then review before we carry on to make sure, double check that we're on the same page. Let me give you a few problems here. Let me ask you to please tell me, is 144 a perfect square? So the question is 144 a perfect square? What do you think? Remember what we know about perfect squares so far. Is it a perfect square? And there's a question you should be asking yourself to try to find that. Okay. And if you found that one, I'm going to also challenge you with 30, just down below here. Is 30 a perfect square? Ooh, I see someone say yes. 2 now say yes. Very good. How do we know that? Well, I can pull up my table here. So this is definitely a yes. Great job, everybody. So this is a perfect square. And what I can do with this table is just add some of that information. If I find my pen here, right, I can find 10 times 10. I know that very quickly. That's 100. If I just carry this on for a little bit more, 11 times 11, I see it appearing in the comments. This one is 121, and you guys are telling me that 12 times 12 is the 144, and that is absolutely correct. And so since I can obtain 144 by multiplying 2 whole numbers, well, one whole number by itself, and I get the 144, I have a perfect square here. However, what we don't see in this table, just from observing, we don't see a 30 appearing. We have a 36, we have a 25, but the 30, which would appear naturally within those two numbers, is not on this table. And so that's exactly right. We have a no for this second problem, right? This one is not a perfect square. This one was, and we said we can have 12 times 12 here. Okay. Let me then ask you, we've looked at perfect squares. Let's then review briefly square roots. How about you guys tell me, what is the square root of 64? What is this equal to? I'll give you a few more. 49. Without pulling up my table again, I'll give you 4 exercises here. What are the square roots of all 4 of these? Perfect. You guys are wonderful. Thank you for always participating with me here. I see 8 appearing for the first one. Love it. I'm going to include that there. That's exactly right. Beautiful. How about we jump to the next one? What is the square root of 81? This one here. What is the square root of 81? I'm seeing a 7. 7 applies to this one here, so I will fill that in. I'm seeing 9. Very good. 9 is here. And what about this one here? Slightly cut off, but we did see it just a few seconds ago. It is 12. Remember, we looked at identifying whether 144 was a perfect square. We said it was. If I pull up the table here, we proved it because we said 12 times 12 gives us that 144. Perfect. Looks like we're all on the same page here, understanding what square roots are, how they relate to perfect squares. So now, as I said, the question is, of course, well, how do we find square roots? I can turn to my friendly phone over here. I can pull up a calculator and definitely find them, and we'll talk about how that comes into play in mathematics when we work with extremely large numbers. A calculator and a computer can definitely be our friends, but there's no need to turn to them when we're working with relatively small numbers. So let's see, out of curiosity, what these computers do behind the scenes to find the square roots of these numbers. Okay? So as we saw, we know how to find perfect squares. We don't need to have that conversation anymore. We know how to find perfect squares, right? We have to rely on some sort of multiplication, and in many cases, if we move to larger and larger numbers, long multiplication. Maybe not the funnest thing to do, but the fact is it's very, very easy to find those perfect squares. Just got to do that multiplication. And that's why we're going to be focusing primarily on finding the square roots of numbers today, and some tips and tricks on how to do that. So one thing I just want to observe with all of you before we carry on, this is going to be a very useful observation. is that when we multiply two numbers together, which let me put this on the page here. So let's say I have two large numbers being multiplied, right? I know that in this case, I'm going to have to perform really, really long multiplication here. That's not the purpose of today, so I'm not going to carry it out for ourselves, but I want us to observe something here. And I want you guys to help me out. What would be the last digit of this product? What do you believe would be the last digit of this product? So without me necessarily having to complete the long multiplication right now, we'll do it in just a second. Not going to be the purpose of today's lesson, but we'll do it just to confirm what we believe is true. So if I were to perform this long multiplication, what would be the last digit of my number? What do you think? Oh, very nice. I see the number appearing. Very good. I wonder how you got it, if you care to share. I'll give people a few more seconds to think about what would be the last digit of this product. What do you think? While you're thinking about that, I'm just going to make this smaller and carry out the long division. Or you know what? I could squeeze it in here. Just use smaller numbers. So I'm going to carry out my long multiplication. I won't necessarily talk through it, but I'm going to show you what I'm doing. Okay. All right. And then I have this. Then I have this. So my final answer, my product here, and I see you guys are getting it right away, is 27,756, and as you guys are seeing, the last digit is a 6. How did you know that before I even finished this long multiplication? Well, some of you might have already thought about what happens during a long multiplication, and you understand that when you move to the second line, the third line, the only numbers that will ever be under this first number, which we'll talk about in a second, will be zeros. And so when you add up every number in that column, you'll always get back only this number. Now, how did we get this number? In this case, a 6. All we did is we multiplied 3 times 2. The ones digits of our two numbers that we were multiplying, right? 3 times 2 was 6. That 6 stayed here. Every other number under it would have been a 0. And so the last digit of my product is a 6. To summarize, it is the number that you get when you multiply the ones digits, the values of the ones digits, and the two numbers you're multiplying. Okay, so let's review that. Let's see what you guys can tell me about without performing the long multiplication. 369 times 41. Please tell me what the last digit will be there for the product. Let me give you maybe two more. 48 times 48. My apologies. And let me give you a funky one. What would be the last digit here? Right, what do you think? For 369 times 41, I'm not actually going to perform the long multiplication, but I'll put in the circle here the last digit. How do we get it? Oh, you guys are sharing it. Wonderful. That's exactly right. We summarized this observation that we made earlier, that if I multiply the value of the ones digits, I get 9 times 1, which is 9, which will also be the last digit of my product. Perfect. There's a 9 there. What would be the next one? Okay. I'm seeing the right answer. So you guys are saying, oh, someone listed it out perfectly. Yes, that's right. So for 48 times 48, I don't care to do the long multiplication. I just look at, okay, 8 times 8 will give me 64. That last digit is a 4, which is also the last digit of my final product. Beautiful. And this little funky one that I got for you guys, a little bit of a challenge, maybe, maybe not. What do we have here? 23 times 29 times 3, I can look at just the ones digits, and I can do it in an order if I need to. So 3 times 9 is 27, and then what would I do? 27 times 3, or the 7 times 3 from the 27, I would get 21, which means that that final number is a 1, or that final ones digit value. Beautiful. We're going to keep that observation in mind and put it together with the fact that we could have noticed something from our table earlier. So let me put this back on the board here. And I want you to tell me something about the ones digits of these perfect squares that we have here. So take a few seconds to just observe these perfect squares that we listed out in this table. What do you notice about their ones digits? Give you a few seconds to think of that. And primarily focus on the ones just above here. So the perfect squares formed from using up all our digits 0 through to 9. Okay. Here, and maybe I'll use my red marker on the side, the last digit was a 0. The last digit was a 1, a 4, 9, 6, 5. We had a 6 again, so I won't write that down just yet. We had a 9 again. We had a 4 and a 1. So all of the answers from multiplying all of the digits by themselves will end with one of these digits: 0, 1, 4, 5, 6, or 9. All of those perfect squares. Great, you guys are observing that beautifully as well. So what does this tell us, right? Since a perfect square is just a number multiplied by itself, right? We multiply that number times itself. The last digit, putting that together with the observation we just made, the last digit of a perfect square must always be, I should say, one of these digits. Okay? And so we're just putting those two facts together. So I can ask you a question, for example. Let's see. If I ask you 441. Do you know if this is a perfect square or not? Let me actually help you out by listing out those digits here. So we said it has to end with one of these digits. So let's say I ask you now 441. Do you know if this is a perfect square or not? Is there enough information here for you to tell me if it's a perfect square? Okay, I see the square root appearing. Very good, which means it is a perfect square. How about you think for a second, how do I know that? How do I know that very quickly without necessarily maybe even memorizing my square root facts? How do I know that? It is 21 to the power of 2, as you wrote. 21 times 21. Very good. Okay. You guys are saying yes? All right. It is, in fact, true. Let me use my green here. It is a perfect square. Very good. And it is, as someone pointed out for us, 21 times 21. Okay. Very good. And I know that because it, of course, ends in a 1, which is one of the digits here. So let's say I give you then 4,567. Do I know if this is possibly a perfect square or not? Right? I don't know for sure, but do I know if it possibly is or not? Very good, Sarah. Thank you for sharing that. Yes, because there's a 1 at the end, so it's a possible perfect square. And then you guys were sharing with me that it is, in fact, 21 times 21. Very great reasoning. What about 4,561? What do we observe about this last digit here? It is a 7. Is a 7 included in one of these digits here, which we identified as the ones digits of any perfect square number? It's not there, right? So right away I can say, nope, there's not even a point in trying to figure out, is there a number multiplied by itself that can get me to this number? The answer is no, because I have here, not a whole number, right? Because it ends in a 7. Okay, let's maybe do 2 more just to make sure we understand that concept there. I'm gonna leave you with 363. Go ahead and tell me that. Okay. Then I'm gonna challenge you with this question. While I write that out, I want you to think about the question above. Let's go see that. I see no appearing for 363. Very good. Okay, very good. It is a no because I have it ending in a 3 and 3 is not in my list. Very nice. Okay. Now I want you to look at this question here. So 841 is the perfect square. I'm telling you that it is the perfect square of a number between 25 and 30. What is that number? What do you think? So I'm telling you it is the perfect square of a number between two whole numbers. So we know that there is some whole number multiplied by itself that gets me to 841. Angela, very, very good question. So you're asking, but what about a number like 21? That's a great question, right? It does end in a 1, and 1 is listed in these numbers here. So listen to the way that I've been wording it, hopefully every single time, and I apologize if not, if it's not been consistent. But the messaging here is that if it ends in one of these numbers, if the ones digit is listed here, then it is possibly a perfect square. So that's great that you're asking about a 21 because it does end in a 1, okay? So we'll take a look at how to find those square roots in just a second. Those are what we would call not so friendly numbers to find the square root of. So let's go back to this question before we move on. How do we find it? Well, we make the observation that 841 is ending in a number 1, okay? So we can possibly look at 25 times 25, 26 times 26, 27 times 27, 28 times 28, 29 times 29, and 30 times 30. However, a few of those we can eliminate right away, right? If I go back to 25 times 25, so I'll write this out here. Remember what we talked about, these last digits, this observation that we made, this pattern that occurs, right? If I multiply 25 times 25, the last digit here is going to be a 5. How do I know that? 5 times 5, that product ends in a 5, right? But the last digit here is a 1, so right away, that gets canceled out. I'm not even going to bother with that. I know that that is not going to get me to 841. Wonderful. Let me look at 26 times 26. And this is all something that I can do in my mind, but let me just show it what I'm thinking here. Great. Let's look at 26 times 26. 6 times 6 gets me to a number that ends in 6, 36. But my number does not end in a 6. Out. 27 times 27. Okay. What am I going to get here? 7 times 7 gives me 49. 49 ends in 9. It is not a 1. Out. 28 times 28. 8 times 8 is 64. That's still not close. 29 times 29, and I see you guys are helping me out already, is my winner. And why is that? 9 times 9, you guys already helped me out with this table earlier. You told me that 9 times 9 is 81. 81 ends in a 1. And so that's how we get the 1 in this number here. All right, there we go. So it is 29 times 29. And it was just helpful to know, obviously, this information. Half the time you're going to encounter these problems, you're not going to know all of this. But this is a step closer to understanding how to find what the square root could be, right, when you have some of these pieces of information. So let's maybe look at that one more time. Let me give you this problem here. I am going to tell you that 4,489, so we're not going to be scared anymore of these large numbers because we have an approach on how to tackle them. 4,489 is a perfect square. I'm telling you it is. And it is the perfect square of a number that is between, I'm just going to write it down here, 65 and 70. Not writing down the entire question here, but I'll repeat it one more time. 4,489 is the perfect square of some number, and that's what we're trying to find, that number, of some number between 65 and 70. Let's try to do very minimal work on the whiteboard here to know right away what the answer is. What number multiplied by itself gives me this one, such that that number is, of course, between 65 and 70. Oh, I see it appearing already. 67. Very good. How do we get 67 really quickly? Well, all I have to do is think about a 5, a 6, a 7, an 8, a 9, and potentially a 10. Which of those give me a product that ends in a 9? Well, we've already done so much practice with perfect squares today. I know that it's going to be a 7, right? I know 7 times 7 is 49. And that 9 helps me out with this final number here, right? So it is, in fact, 67. Cool, right? It means that we can work with these larger numbers without having to turn to our calculator, and we can do this really quickly. Again, this is a little bit easier because I'm given a lot more information than I normally would when I encounter some of these problems in the real world, but that's okay. It means that we know how to work with it if we have this information. All right, let's look at some tricks to squaring before we look at the ultimate lesson or the ultimate takeaway from today, which will be new to most of you, I guarantee it, and it'll be the coolest thing that you see today. I highly guarantee that as well. So let's look at tricks to squaring, right? As I said before, we don't have to have too much of a conversation on finding perfect squares because that turns into a conversation of doing long multiplication together, right? That's not necessarily what we want to focus on today, all right? However, there are some tricks we can do such that we don't even have to do the long multiplication on our sheet of paper or on our whiteboard. We can do it all up in our minds here, right? We can be computers ourselves, right? Again, not having to turn to the calculator to find the squares of some of these larger numbers, right? So the two tricks that I want to show you is if you have numbers that end in 0 and if you have numbers that end in 5, right? There are tricks where you can find these squares very, very quickly. So let's say that we take 70, okay? 70 is, of course, a number that ends in 0, so that's the trick that I'll show you first. This is very, very simple. This is a very cool magic trick that you can show all your friends after today, okay? Let's say I take my number that ends in a 0. What I'm going to do is write down 2 zeros right away, okay? Because this final product, this final square, is going to end in 2 zeros, okay? Your answer will always end with double zeros, okay? Then to find what comes before the zeros, what you're going to do is square the digits before the 0. So this is your digit before the 0. It's a 7. We know how to square 7. We saw it on our table. We saw it already in a few other problems. 7 times 7 is, of course, 49. And all I do is I write that in front. Right? And you can double check that if you really needed to. You can perform the long multiplication, 70 times 70. But I guarantee you're going to get back to this answer here. And it's as simple as that. Okay? So I can show you many, many more, or I can ask you to do many, many more. Please find for me the square of, let's go a bit bigger. Find the square of 120. And some of you have shown me that you understand exponents already. For those of you that don't get too scared here. This is just another notation that we use in math, right? But it really just means that I'm looking at 120 times 120. So whichever way you have to look at it, go ahead and look at it that way. But really what I want you to find for me is the square of 120. How do I get that? Well, it's a number that ends in 0. Sandra just told me that any number that ends in 0, their square is going to end in 2 zeros. Okay? And how do I find what's in front? Well, I take the digits that are in front of the 0 in that original number and I square them. Wonderful, I'm seeing the answer appearing. 12 squared. Again, that's something we saw earlier today. That is 144. I just include it in front of the 2 zeros. And the way that you guys are probably used to seeing this number is 14,400. All right. Maybe with a comma, maybe just with a space. Regardless, it's the same number, 14,400. Let's do one more just because it's super fun to see that we can perform these computations so quickly when they're so large. Let me just erase that whole thing. I'm going to give you one more. I am going to ask you to find the square of 110. Let's do this super quickly, right? 0, it ends in 0. Perfect. My final answer is going to end in 2 zeros. Then I look at the digits in front of my 0. It's 11. Again, something we saw before. 11 times 11, or in other words, the square of 11. 11 squared gives me 121. Ta-da! It's math magic. We get 12,100, right? Go away, calculator. We don't need you. We know how to do these computations very easily on our own. All right, so those are numbers that end in 0. Let's look at numbers that end in 5. Again, we can use tricks to find these very quickly, right? So let's say that I want to take, what's the example I have here? I have 35, okay? So I want to find the square of 35. Again, for those of you that have worked with exponents already, I'll show you how this applies here. I just want to find the square of 35, okay? So what you're going to do here is follow this process. So write down 25. Your answers in these problems will always end in 25. Before they always ended in double zeros. Here they end in 25. Alexander, that's awesome. Math magic. That's exactly what this is. Okay. Then we're going to look at the digits in front of the 5. Remember before we looked at the digits in front of the 0? Now we look at the digits in front of the 5. Okay. So in this case, we have a 3. What we're going to do with this 3 is we're going to increase this by 1. So 5, if you listen to that language, 3 increased by 1 is a 4. And what we do with that number, the 4, that product, is we multiply it by the original digit, which is a 3. Okay? So let me maybe write that down here. So if I increase this by 1, that gives me a 4. Okay? So what I'm going to do is I'm going to multiply this 4 by this 3. So let me maybe show you this way for those of you that really want to follow along visually. So I'm taking this product, and then I am taking the original digit in front of the 5. That's this guy here. Okay. I know this. It is equal to 12. So let me just, no, that's fine. And then I just take this 12 and I place it again in front of the 25. So in this case, I have 1,225. So a little bit trickier than before, but you can see the idea is almost the same, right? We're putting some number in front of either a double 0 or a 25, and we're multiplying in the process. Okay, so let's look at maybe 2 more examples of this. So let me ask you instead to find the square of, let's stick with the smaller number, and then we'll move on to a 3-digit. Let's say I want you to find the square of 15. Okay. It's a number that ends in 5. Sandra said then that product, that square is going to end in 25. Then what I do is I look at the digits in front of the 5, which is a 1. I increase them by 1. Then I multiply this product by the original digit. So in this case, I get 2 times 1, which is a 2. And then I place that in front of the 25. And my final product, my final square, is 225. Pretty cool, right? Some stuff that I never got to see in the classroom before too, but pretty awesome to find as opposed to having to resort to long division, long multiplication. Let's do one more just for fun. Let's say I'm going to give you a bigger one. Let's do 125. I want to find the square here. Give you a few seconds to help me out with that one. It ends in a 5. So I know that on my final answer, my final square is going to end in a 25. Then I have to find what's in front of this 25. We made an observation. We look at the digits in front of the 5. Even if it's 2 or 3 or 4, we keep those together as one number. We increase by 1. Then we multiply that product, or I'm sorry, have I been saying product here? We multiply this sum by the original digits. We multiply to get what comes in front of the 25. And I see some of you have already helped me out with that. That's exactly right. Thank you, Alexander. Yes. So here we would get 156. All right. And so that just goes in front of our number here. And again, ta-da, math the magic. However way you want to represent that number, however you've been taught to in the classroom, 15,625 is the square of 125. No calculators, just my brain. Pretty cool, right? Pretty cool tricks to doing this all on our own. Go ahead, go to your nearest Mathnasium and show them that you know how to do a lot of this computation in your head. Show them these tricks. Impress your friends, your family members, okay? So let's put that to the side right now. We've looked at some of these tricks, but let's go back to this conversation of trying to find the square roots, right? So let's say that I want to find, the square root of 576. Let's do that. I want to find the square root of 576. Take a few seconds to think, how would we possibly find the square root of a number like this, right? This is where it gets a little bit challenging for me, let's say, right? I don't have this effortlessly ingrained in my mind that I can effortlessly recall, right? I don't know. I can find the square root of 81 fairly quickly, 144, but then as we start to get to really big numbers, I haven't necessarily sat down and memorized them or encountered them enough to really have them in my mind ingrained so that I can just pull them up whenever someone quizzes me. So how can I possibly find the square root of this not so friendly looking number? 576. What do you think? Okay, so let's start to make some observations about this for now. Let's just take some approach. And if you guys want to share what you think, go ahead. I'd love to see it. But let's look at one thing first. Let's at the very least determine what the square root of this number will be between. Look at some whole numbers. And we know that we might get into something ugly here, possibly a decimal. I don't know just yet. Let's just see what happens. So let's determine which two tens numbers the square root of 576 is between. So for example, if I start to look at 40 times 40, okay, remember we just looked at finding the squares of numbers that end in zeros. So I know very quickly that this is going to be 1,600 or 1,600, right? We can break up the numbers. Yeah, that could be one approach. Be interested to see how you might do that. But let's start to make some observations here. So this is too big, right? This is 1,600, or in other words, 1,600. 576 is pretty far away from that. So let's see if I could get a bit closer. 30 times 30. And note that I'm sticking with tens numbers for now because I just saw a trick for finding them. So again, I don't have to resort to a calculator. I can do this all in my head very quickly. I know that this gets me to 900, so that's a lot closer, but it's still too big, but it's closer. So let's go to 20 times 20. All right. Here I get, oh, I know the trick here. I get to 400. And this is too small. But I know that the numbers have to be, or the square root, will be somewhere between 20 and 30. Why? Because 576 is between 400 and 900. Okay, great. I'm on the right path. I know I've now narrowed down what could be such a large list, a long list of numbers that I could possibly be working with here, to now only the numbers that are in between 20 and 30. Perfect. Okay, so now let's work with the fives, right? So now let's determine if it's between 20 and 25 or 25 and 30, this square root. So I've established this. I'm going to remove it. Let's now start to look at 25 times 25. What do we get here, right? Using the trick from before, I know it's going to be 625. Okay. And that is bigger than 576, right? Which means to me that the square root of 576 is actually going to be somewhere in between 20 and 25. Right? Putting those two facts together from what we found before. Perfect. So I'm going to summarize that for myself here. Between 20 and 25. Okay. At least I'm that much closer. And I see the right answer appearing just right now. I see in the comments. Beautiful. That is right. But let's see how we get there. Okay. I've narrowed it down. Now, we know, I'm going to tell you right now, that 576 is a perfect square. So let's use that knowledge, right? It is a perfect square. right? Which means that it is going to end in a digit, what we saw before, 0, 1, 4, 5, 6, and 9, right? In one of those digits. And so we've already actually encountered problems like these, remember? We said if we know that this is a perfect square, and then we know that its square root is going to be in between some two whole numbers, all we have to then do is look at 20, 21, 22, 23, 24, 25, and see which of those multiplied by themselves gets me back to this number underneath the square root sign, right? And actually, I don't even have to do all that log multiplication. That's the best part. I can just make this observation about the last digit, right? 20 times 20, it's going to end in a 0, but this ends in a 6. That's out. 21 times 21 will end in a 1. That's out. 22 times 22 ends in a 4. Nope. 23 times 23 ends in a 9. Nope. 24 times 24, right? 4 times 4 is 16. 16, of course, ends in a 6. This ends in a 6. So that's what I'm working with. All right? So I didn't have to do too much math here. Now I know that since this is this perfect square, I told you that it is, then we know that its square root is a 24. All right? And we can do that a few more times, right? We can look at, let's say, the square root of 961. Okay? I'm going to tell you that it is a perfect square. So how do we go about that? Let's find two numbers that it's between, so two tens numbers. So if you do that work, I'm just going to tell you right now, it's going to be between 30 and 40. Okay. Can I narrow this down? Yes, I can. I can actually narrow it down. If I do the work from before, I can narrow it down to 30 and 35. Okay, and you guys can do that work on your own on your page just to verify that my math is in fact correct, right? Now, knowing that the square root will be between 30 and 35, all I have to do is look at the last digit of any of these numbers that are in between here, right? And it happens fairly quickly. 30 times 30, that's going to end in a 0. That's wrong. I have to end in a 1. But 31 times 31 will end in a 1, and so I know that that is the square root here. Okay, pretty cool, right? I didn't have to do, too much math here, but I am doing math at the end of the day, and it doesn't even look too much like it, right? There's not too many numbers that I'm working with on my page because I'm doing it all up in my mind because we're doing our best to work with friendly, nice numbers. So let's maybe observe a few of those cases where they're not so nice, right? Of course, the world isn't always going to work in our favor and give us these beautiful numbers to work with. Math isn't always going to be that nice to us, right? But we can be nice to ourselves in how we approach it, right? And so remember that sometimes when we take the square root of a number, we're unfortunately not going to get a whole number. We've been encountering those scenarios here. Beautiful, they've made us happy. But in some cases, we're actually going to end up with a decimal, right? And it's not going to be even a nice decimal. It's not going to be something that we can rewrite as a fraction or a terminating decimal. They are actually going to be, if you've heard this term before, irrational numbers, which means numbers where their decimal representations will never terminate and never repeat, right? Those are, and some of you might view this as the most beautiful numbers in the world, and others might view it as, unfortunately, numbers that I don't want to encounter too much of because they just create a bunch of chaos on our page. Whichever way you want to look at it doesn't matter because we're still going to have to work with them. Some of you might know already that the most famous irrational number is pi, and so, they could be just as beautiful as the other numbers that we work with. So let's look at, for example, if I wanted to find the square root of 27, right? I know from the table that we worked at before, just let's make an observation, it's not going to be, the square root is not going to be a whole number. How do I know that? Because 27 is, of course, between 25 and 36, and the two whole numbers that create the 25 that multiply to be the perfect squares of 25 and 36, I've already used them up, right? And so we know that the square root of 27 has to be somewhere in between 5 and 6, right? It's going to be some some decimal that we can find possibly using long division, okay? So at the very most, what we can identify, as we saw earlier, is what that square root number will be between, what's two whole numbers, right? But then the question becomes, well, how do I actually find that without having to turn to a calculator, right? So let's look at this a few different ways, two different ways. So let's say I want to find the square root of 441 exactly, okay? I want to work with that. One way that we can do this is to look at some of the prime factors. And for those of you that have looked at prime factorization before, this won't be too new for you. For some of you that haven't, just a really quick review of what a prime number is. It is going to be any number whose factors are just 1 and itself, okay? So let's look at that. Let's find the prime factors here. So if I want to find one prime factor of 441, I can say, for example, that 3 is a prime factor, okay. Right? Why? Because I know that 441 is 3 multiplied by 147, okay? And I know that 3 is a prime number, okay? Then I'm just going to carry on with that, right? Let's look at then 147. Can I find two numbers that multiply to 147 such that one of them is a prime? Well, I can find that. I'm just going to, rather than repeat it, use these guys here. 3 is a prime factor again, because to get 147, so maybe I'll write this out here, that gave me to 441, I can multiply by 49. Okay. And then, of course, 7 is a prime factor because, of course, I know how to find 49. We looked at it earlier with the table that we had. 49 is just 7 times 7, right? 7 times itself. Which means, and again, for those of you that would have seen prime factorization already in the class, what I can conclude here is that 441, I'll write this up here, is equal to a product of all of those prime factors, right? So in this case, I have 3 times 7 times 7. Okay? And we can have a separate conversation about prime factorization during another lesson, but that's essentially how I found that 441 is just a product of these prime numbers. And why is that useful? Well, if we know anything about a perfect square, it is a number multiplied by itself, right? To get me to that perfect square, which means that instead of looking for the square root of 441, we can look at it as finding the square root of 3 times 7 times 3 times 7. And if you see, I actually moved around my numbers because what I can write here, let's use a multiplication sign here, is I am multiplying two numbers by a number by itself, right? 3 times 7 is 21, and 3 times 7 again is 21. So what's happening here is 441 is just equal to 21 times 21, which means that the square root is, of course, 21. How cool is that, right? So if we're able to take the number that's under the square root and write it out as two pairs that are the same, then we know fairly easily what the square root is. Again, I kind of cheated us here, right? I chose numbers that gave us something this pretty. Once again, in math, we're not always so lucky to encounter numbers that will be so friendly to us. So let's look at one more example, right? This is a friendly case still, believe it or not. Okay, let's look at one more and then we'll end off for today. Let's say I want you to find, and I have one prepared here. Let's say I want you to find, let's work with something bigger, the square root of 24. Okay, so someone asked earlier, what about the square root of 21? It ends in a 1, so the 1's digit is part of the list, same as the 4 here, but it's not part of our table, so we know that there's not a beautiful whole number that gets us to that perfect square. How do we find the square root of a number like this? This is where it gets the most complicated for today, but I promise you it's doable. I might have to write this down a bit lower. Let me do that. This is where we really have to concentrate and follow the process. So here what you're going to do first is write out your square roots. You're going to right away include a decimal and pairs of zeros. That's your first step. Extend this. Your next step is to think, okay, what is the closest perfect square to 24, but lower than it, smaller than it? 25 is very close, but it's slightly higher, so that's not good. So I know if 25 was 5 times 5, 4 times 4 would be the closest, but below it, which is 16. So we take the square root of that, which is a 4, and we include that just here in the quotient, right? And just here. Okay. Again, I found this 4 because the closest perfect square to 24, but less than it, is 16, and the square root of 16 is 4. Carry out the process as you normally would with your long division. So I have 4 times 4, I multiply to get 16, and then long division tells me to subtract. So I get an 8 here. Okay. And I'm almost going to repeat the same process. So I'm going to include my zeros here. And I'm going to I'm going to perform division here. And the way that I do this is I am going to, sorry, I'm just thinking here. I don't want you guys to get confused with the way that I'm writing the division and the square root, right? So we're looking for the square root of 24, but it involves some long division here, right? So now I want to look at this number 800. And what I want to divide it by, my divisor, is going to come from multiplying what I have here in my quotient, multiplying it by 2, or in other words, doubling it, which is an 8, and then having a placeholder. I don't know yet what this number here is. I have to find it. So this is where it gets the most tricky, I promise. So now I have to play around with 80, 81, 82, all the way to 89, right? And I have to try to find some number where the last digit multiplied by that digit as well. So it could be 80 times 0. It could be 81 times 1. I'll squeeze in one more here, 82 times 2, and so on. I need to find something that fits these patterns here such that I get as close but below this number. So for example, I'll show you that in this case, it's actually 88, because 88 times 8, okay, gives me 704. When I subtract that, I get 96. And then you're just repeating the same process, right? So let's say that I wanted to just find it to the nearest hundredth, and then we'll be done for today, right? So far we have 4 and 8. So 4 with a decimal 8 here. And so let's say now we wanted to find just to the 100th spot, right? Or let's say I even wanted to find the 10th place. I need to find what's going to be in my 100th place. So let's perform this one more time. So the process is I'm going to bring down 2 zeros, and then I'm going to double what I have here. Ignore the decimal for now. So if I have 48, that doubled is 96, and I include a space here. And again, I start to think, okay, so 961 times 1, 962 times 2, 963 times 3, and so on. What product do I get that's very close to 9,600 but still below it, right? And I'll give you the answer there. It is actually our highest number, 969. So again, I include those two here. 9 times 969 gives me 8,721. I did the math earlier, so I'm just looking at the products that I found earlier. And then I subtract and I carry on. So depending on how many decimal places you needed to find, you would just carry out that same process continuously. So what I've done is we will share with you a packet of exercise problems for you to practice procedures such as this, where you're trying to find the square root of numbers I'm going to call not so necessarily friendly. but then also resorting to some of those other processes that we looked at before. Hopefully you had a lot of fun with this, and I hope that at the very least this was something new for you, because I'll definitely admit that this is something that I never got to see in the classroom. To be honest, I don't think that as a student in elementary or middle school, I would have necessarily been, I don't even want to say interested, but if I'd necessarily find this to be something fun or easy to do. It does seem a bit complicated, but definitely practice with this. And the best thing about this, and the way that I always like to look at what I'm learning in math, is why is this important, right? It's worth asking. And so I talked to some of my friends earlier about this, and I thought, why does this fascinate me? And I came to the realization that it's because this is what computers do. You know, those things that we're on every single day? They do this so quickly. And so looking at all the math that I'm doing on this page here, this had to be taught to a computer to be able to do it so quickly, right? And isn't that just such an amazing thing? Is our human minds are capable of doing so much, and looking at these patterns and finding all these complex things in math. We teach a computer to do it, and then that computer can do it faster and faster. The reason it's so useful for us to know what happens behind the scenes as mathematicians, or mathemagicians as we've established today, is that then we can teach computers to do so much more, right? I'm going to end it off for you guys for today. I'm sure you've had enough of listening to Sandra for today, but I hope that you had fun. I hope that you explore this more in depth. Go and show this off to your next Mathnasium instructor, your friends, your family. Have a wonderful day. Have an enjoyable rest of the week, and I will see you later today. Bye-bye.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.